Okay, Assalamualaikum and good morning. So today we will have discussion about the type of blades. Okay, previously in our lecture notes, we already discussed about the velocity triangle, and the velocity triangle is depend on the type of blade. So today I will show you three type of blade, which is the forward blade, the radial blade, and the backward blade. So please make sure that every time you solve problem for centrifugal pump, please make sure that you could draw velocity triangle based on the blade mentioned in the question. So this is the forward blade and this is the velocity triangle that you should draw. Okay, how to classify, how to determine whether the blade is forward, radial, or backward. Okay, the idea is simple. If you see this is the blade, so and then for sure you could determine the rotation. So this is the rotation of the blade. So and then you just imagine that you stand here. So because it is moving counterclockwise like this one, so make sure that you are facing the same direction. So if you stay like this, you will find that this part, this spoiler, this part is actually stay in front of you. So we could call this blade as the forward blade. Okay, that is the idea. So and then if we see the radial blade, it is quite simple because at the outlet here, so it goes straight as like a radius and like in radial direction. So it is quite simple for you to classify, to determine the radial blade. So and then the third one is the backward blade. So backward blade, you do the same idea. So you just determine the rotation direction here, and then because it's moving from right to left, so you need to stay here, stand here and looking forward there. So you will find that the blade here is actually at your back. So we could call this as the backward blade. So this is a very simple idea for you to determine the backward, the radial, and also the forward blade. Okay, so we go for the forward blade here. So I would like to show how to draw the velocity triangle for forward blade. So again, it starts from the same step. So first you need to draw the blade here. So and then you determine the rotational speed. So after you determine the rotational speed, and then you need to draw the actual velocity. So the actual velocity is here. So because it's rotate from right to left like this, so the actual velocity is actually comes in like this. So and then the actual velocity, let's say, goes out like this one. So please write your actual velocity first. So and then now you could draw the component velocity. So usually we draw for the component velocity that reflect to the shape of blade and the rotational speed of impeller. So because the shape is like this, so we could draw the velocity component relative to the shape of blade like this one for inlet and like this one for outlet. So and then, okay, we could draw the U1 is like this, and the U1 here is like this. Okay, I think it is okay for me not to explain the reason, okay, because we already explained it in previous lecture. Okay, in this here for forward blade, okay, please make sure that you draw the relative velocity for the blade here is between the VF2 here and V2. So this is actually the things that you need to remember. Okay, so and then, okay, because this is the velocity vector, so you need to start your U2 here, okay, at the end of VR2 line. So this is the rule of thumb to draw a velocity vector. So I hope you could understand this. And then another thing is, please bear in mind that the velocity vector is actually closed loop, the closed loop, the resultant velocity. So means that if the resultant velocity is start from here to here, so means that the component velocity need to start from here to here and then continue from here to the end point at here. Okay. So now you draw the first component velocity. Next, we draw another component, okay, which is related to the ideal condition. So again, please make sure that the velocity vector that you want to draw is based on the velocity, based to the resultant velocity, which is the absolute velocity here. So, and then for actual velocity, so we could draw that. So in theoretical idea, so the actual velocity is straight like a radial, in radial direction. So we draw the VF1 here, and also we draw VF2 here. So, and then why the actual velocity is not similar, is not same with the theoretical, with the ideal velocity, because there is turbulence, there is a whirl. So we draw a whirl from here to here. Okay, and then at this one, so you have the V1, V whirl 1 at the bottom there. Okay, so in this, okay, the forward blade. So what is the main character of the forward blade? So we found that the angle here, so mean the angle for the blade is actually more than 90 degrees. So this is the characteristic, the main characteristic for the forward blade. So if the question asks you to describe about the forward blade and so on, please make sure that you write this one. Okay, so this is the main idea for the forward blade. So I hope you could snapshot this video, so you could make sure that you could draw velocity triangle for the forward blade very well. So we go for the radial blade. Okay, this is the image for the radial blade. So how to determine the radial blade? So at the outlet here, the shape of the blade here is, okay, is parallel with the radial. It's in the radial direction. Okay, so how about this one? This is not straight. Okay, please bear in mind the radial, the blade type is actually determined by the output blade, by the shape of blade at the output region. Please do not see the shape of blade at the inlet region. Okay, just see what the shape of blade at the outlet region here, and then determine the type of blade. So if it is goes straight like this one, so it is the radial blade. Okay, this is because sometimes students confuse how to determine the radial blade. Okay, at the outlet, so it goes straight there, and then I think you already know. So we know the blade, we know the rotational speed, and then we need to determine the absolute velocity, the real velocity. So this is the real velocity V1, and this is the real velocity V2. Okay. So, and then we could draw the component velocity. So this is the VR1, okay, and this is the U1. Okay, so and then we could draw, this is the theoretical, the ideal velocity at VF1, and this is the V world 1. Okay, so and then, so this is the velocity triangle at the inlet. So it is same with previous type of blade, forward blade. So there is not much, there is no difference. It is totally the same. Okay, however, at the outlet here, okay, so we need to split. We need to split the actual velocity V2 into its component. So first we split into the component of blade angle and also the impeller speed. So we found that at the outlet here, the angle is 90 degree, so we draw velocity here is straightforward like this one, because the shape of the blade here is straight like this. Okay, so and then we connect this one into this one, and then we draw these as the U2, means the velocity components that reflect the rotational speed of the impeller. Okay, so and then we draw another component which is related to the theoretical velocity and also the turbulent. So in this situation, we found that, okay, the VF2 here is actually at the same direction and the same magnitude with VR2. So it is okay for you to write the same vector. So again, and then we need to close loop this vector. So we draw the V2 like this. So means that for radial blade, okay, the value of VR2 is equal to VF2, and the value of U2 is equal to V2. So this is the another characteristic for radial blade. And then if you talk about the blade angle, so you could write that for radial blade, at the outlet, the angle blade is 90 degree. So this is the characteristic of the radial blade. So and then we go for the third one, the backward blade. Okay, this is the most common question using the backward blade. Okay, so the backward blade, okay, I think we could go faster here. So you know the shape of the blade like this one, and you could determine the rotational speed like this one, and then we could determine the actual velocity. So this is the actual velocity, V1, and this is the actual velocity that goes out at the outlet here. And then we could draw the velocity component for VR1 is here, and this is for the U1. Okay, so this is the VR2, and this is the U2. Okay, so and then we could draw component regarding to the actual velocity. So we could draw the VF1 is here, and we could draw the V world 1 is here, and this is the V world 2 VF2, and this is V world 2. Okay, so and then if you want to draw the component velocity of U, please make sure the rule of thumb is it must be in tangential condition. So this is the tangent for this point. So the U2 here must be parallel with the tangent line here. So again, the U2 here, if you see, so it's parallel with the tangent line here. So that's why you see that this velocity triangle is quite shifted from the other velocity triangle. It is actually the location is shifted, but the way you draw the velocity triangle is still use the same idea. Okay, so and then what is the characteristic of the backward blade here? Okay, so for sure we could see the angle here, the blade angle here is less, not more than 90 degree. So this is the main characteristic for the backward blade. And then you could see here that for the backward blade, the velocity U2 here is actually longer. It's larger compared to the forward blade. So for the forward blade, you will find that the V-wall velocity is actually larger compared to U2 velocity. So that's why I said you cannot just remember all the equation after this. So because all the equation is actually comes from the velocity triangle. So I will show you in tutorial how to use velocity triangle very well to get the equation, because the equation here is actually, you could use a lot of equation based on the velocity triangle, because in velocity triangle we could have we could use trigonometry. Maybe you could use sine, you could use cosine, you could use tangent, and so on and so forth. So this is the velocity triangle for backward blade. So I hope you could snapshot this one, or after this you could watch this video. So and then we go very quick for this one, the effect of blade type. So centrifugal pumps do not always have backward curved vane, but when they do, it is mostly for fluid in the incompressible regime of operation, such as water. From compressible operation of fluid, such as air, forward curved vane centrifugal pumps are used. The net ideal head developed by a centrifugal pump is given by A minus BQ. So this is actually just a note. Okay, so this is how we get the ideal head of the centrifugal pump. So where is the Q here is the volume flow rate at the impeller outlet, and A and B is actually the constant for a given impeller running at a given speed. Okay, but I want to say here is actually, okay, if you explain about the advantage or the disadvantage of the forward or radial of the or backward blade, is actually you could describe from this graph. So this is the head here. Head mean the capability of pump to transfer liquid from lower to the higher level. So and then the discharge here means the flow rate. So if you could see here for backward blade. Okay, so if you increase the flow rate, so means if you increase the speed of the blade to have more water transferred, so you because the cross sectional area of pipe is constant, so if you increase the velocity, so the flow rate will increase. So when the flow rate here is increased, we will find it is actually not contribute to the increment of head. So increment of head means it's not contribute to it means that your pump is actually not capable to transfer water more higher, because this is the characteristic of the backward blade. Okay, you could describe it by from this graph. So and then the idea of this one, so it says that the backward curve is actually uh, normally used for water, and for the forward curve here, forward blade is used for air. Okay, so what is the reason of this one? So you could say, okay, that is this is the blade, so this is the rotational speed. So if it's shaped like this, so mean it is a backward. So this is a backward. So and then this backward, okay, backward, okay, and backward usually used for water. Why? Because water or liquid, it has high viscosity. So the density is high, the viscosity is high. So mean because the density is high means the weight of the liquid here is higher. So if you want to swap the liquid, so for sure the backward here is the best shape, because if the fluid here, okay, if the fluid cannot go through, cannot be swept, it can flow easily to the other side like this one. So you could imagine, okay, it is, and then if you use water, and then you use forward blade like this one, okay, you will find that the water will trap at this region, and because water has high density, high viscosity, so means that water is more weight compared to gas. So it will give a lot of burden on this blade, and the consequences is the blade can be broken here, can be broke here. Okay, that's why we don't use forward blade for water, for liquid. So we normally use backward for liquid, and then we use uh, forward blade like this one for gas. Why? Because for gas, okay, it is easily, if you use like this, so the the efficiency. So means that it seems that this blade catch all the gas here and push it into the rotational speed. So means that the forward blade itself has specialty to catch all the gas and to move and to rotate it in the pump, compare with the water. So with water is very weight, so and then it is not just suitable for the forward blade. So this is the rationale for the why we use backward blade for liquid. Okay, so and then this is actually the notes. We are not going to use this idea. So if you learn more about pump, so sometimes in textbook they will show you one equation like this. So losses is KQ square. So it is actually the simplified frictional losses in pump. Okay, so but we don't use this. Our syllabus is not using this equation. So again, and another thing is that you could say about the difference between the forward, radial, and backward blade. It's actually about the discharge and the head here. So and then what you see just now is actually the graph until this one. Okay, that's why you will have forward, radial, backward. You could see here, so you have the forward, radial, backward. So this is actually the small scale of the graph. So this is the larger scale of the graph. So the first graph is actually telling you about this region only. So if you have a larger region, the the correlation between the actual head and the discharge here, so you will found that the correlation is actually not in straight line, because in previously here you could see that it is a straight line, but actually it is not a straight line. If it is actually curved like this. Okay. So this is actually the actual head, and this graph is actually the ideal head. That's why for ideal head here, you will find it goes straight like this one, while in actual head, it might be a little bit curved. Okay, it is from at this region. Okay, but if you take a at wider angle, so you will find that the flow rate is actually the Q will curve like this one. So what is the meaning of this one is actually when you operate a pump, okay, all pump actually has its own optimum point. Optimum point where it means that you need to find what is the best flow rate that give you the best actual hit. Okay, for example, here and here. Okay, for example, for the forward blade here, so this is maybe the optimum point. So you need to set your pump at certain value of discharge, and then it will give you the highest head that the pump could deliver. So you need to get that point. Why? Because it is not simply by changing the value of discharge you will get the good head, because sometimes maybe you could increase the discharge but actually the head is going down. At the same time, if you decrease the velocity, means decrease the discharge, again the head is also reduced. So means that it doesn't mean that if you change velocity, so the actual head will goes up and up, it become larger and larger. Okay, that is the idea of actual pump performance. Okay, so and then this is the idea of the calculation of power. So power is rho GQH. Okay, please remember this one. And then if you draw a graph for this one, you will find that it is actually give the idea. This is the forward. So and then the radial, and this is the backward. If you see all this graph, it's actually the sequence is actually almost the same. So it is the forward will increase, the radial is something like this, and the backward. So if you increase the discharge, so maybe the power required is actually lower. So actually what I telling you here is, if in the final exam or in test 2, you you need to explain the about the difference between three type of blade. If you asked to draw the velocity triangle for each blade, for example, and then you need to explain the advantage or the disadvantage for each blade. Okay, you could read this. I think almost all of this is actually explained in my explanation just now. Okay, so what I want to say here is actually the comparison of blade type. So we have backward, we have radial, and we have forward. So the all the parameter is explained here. So in backwards, so it is a low volume, but you could run it at a high speed. Again, why you could run it with high speed? Because the backward here will give chance to liquid here to flow like this. So means that it reduce the burden of the blade. So means the blade will not broke. Okay. So and then it is quite stable, and that it is because of the design here, and it is suitable for liquid. So this is the most important. Actually, you could determine whether that pump is for liquid or for gas. Okay, because we not use pump for solid. Okay, we only have liquid and gas. So and then this is the radial. So normally radial, so the rule of thumb is radial is actually the intermediate one. So it has intermediate volume, intermediate speed, intermediate stability, and so on and so forth. So and then normally it used for liquid, because again, as I said, if you have a radial like this, it is not easy for that radial to catch the gas and push it and rotate it. Normally for gas, we are using the forward blade, because this shape of blade is actually give more advantage to the blade to catch the gas and push it and move it forward. So this is the idea of forward blade actually. So and then this is the one. So and then it must be run at a low speed. Why? Because it is used for gas. So you know gas is quite it's fragile, it's light. Okay, if you run so high, so maybe you cannot catch the gas. Okay, so that is the idea actually in very simple words. Okay, okay. So this is the advantage and disadvantage for these three type of blades. So I hope you could remember these and you could explain it very well in exam later on.